Wow, you really start from the ground up. You design these things as well?
We do our own design work, but primarily we're working from custom and stock plans that are given us by our clients. Grab a chair.
So why are you going over the plans?
We're looking for various places where we can simplify the detailing. We have to keep in mind what our own crews are capable of doing. We review the plans with our own operation in mind. And actually, energy conservation doesn't always cost the client more money. It's possible to find places where we can simplify things and make it less expensive.
So what kind of specific details are you looking for?
Well, there are 5 key features that should be used whenever you review any plan, and I think we should review those features.
There are 5 key features that are common to R2000 and energy-efficient houses alike. First, they have higher levels of insulation than a conventionally built house. Second, the houses are built to control air leakage and to be draft-free. Third, because the house is that much tighter, these houses require a mechanical ventilation system to provide a controlled and regular supply of fresh air to each room of the house. The fourth feature is the use of efficient heating equipment. And the fifth and final feature is the use of building designs which make use of passive solar heat.
So as a builder, you're interested in the practical aspects of those 5 things. What about the building design itself? What kind of fundamental principles is the designer concerned with?
Well, probably the most basic fundamental is just the size of the building itself. Heat loss is a function of exterior surface area, so you want to do whatever you can to review the design in terms of minimizing that external surface area if possible. The greater the amount of exposed surface area, the greater the rate of heat flow. The most efficient shapes are those which have the best volume to surface ratio. Domes, cubes. In both cases, these designs allow for the greatest amount of interior space while minimizing the exposed surface area of the house.
Well, you're a pretty smooth talker, but I bet you haven't sold too many domes in the house market.
You're
but
right.
You're saying compact is best.
Compact is best, and also simple is best. You want to minimize the number of overhangs, bay windows, cantilevers, that kind of thing in the building, which isn't to say that the building can't have architectural interest, but we have to realize that whenever you do add that kind of thing to a structure, you not only increase its surface area, but you also make it considerably more difficult to get a continuous vapor barrier into the building.
Now, how far does design extend? We're designing the structure, but what about the entire lot and the positioning of the house and everything? Is that considered part of the design process?
Oh, absolutely. I think that perhaps one of the aspects that we miss most often is the fact that we can achieve a tremendous amount of, if you will, free heating as a result of getting proper southern orientation. Passive solar heating does a phenomenal job. And also, we frequently see buildings that have an awful lot of west-facing glazing. And west-facing glazing can be very dangerous because it tends to lead to overheating.
Well, are there some general guidelines to be followed?
There are some general guidelines that are really worth discussing with your designer. In the average house, the ratio of south-facing glass to interior floor area should be on the order of, say, 6 to 9%. And this alleviates most of your overheating problems. Secondly, windows should be protected from the direct summer sun, either through the use of overhangs or awnings, or even by the clever placement of deciduous trees on the site.
So the designer is concerned with, first of all, optimizing the structure, and also with orienting it to take care of passive solar and things like that. Now, what about the specifics of controlling heat loss through the shell of the building?
Well, that's where we get back to my reviewing the plans. It's extremely important to take all of those things into consideration. The thermal performance of the building is really something that has to be given very careful attention. I'd like to show you how we do that out on the site. David, we're not here by accident. This is a great opportunity for us to show you the various phases of production in obtaining a really good thermal performance in an exterior wall. We normally wouldn't find the drywall on without a roof. Now, we've already looked at the ability to improve the thermal performance of a house by reducing its exterior surface area. What we're going to be looking at now is the way in which we improve the thermal performance of the specific assemblies in the wall and the impact that air infiltration and exfiltration has on that wall assembly.
Well, are we basically going to be talking about insulation at this point?
To a degree, but we're also going to be looking at the way in which you design a wall to function properly.
Okay, so we're talking about the wall as a system. What are the kind of basic requirements?
Well, let me show you.
The framing techniques will be designed to minimize heat transfer from the inside to the outside and will allow for high levels of insulation. The performance of the insulation materials installed will be optimized through good installation practices. Furthermore, heat flows into and out of the house will be minimized by using airtight construction practices.
David, this builder's got the right idea. He's framing with 2x6 because he wants to get a higher R value in his outside wall. But look what he's done. These 2x6s are on 16-inch centers as opposed to 2 foot, and he's put a block in here. There's a lot less R value in the wood than there is in the insulation that's going to go inside this cavity. What we want to do is make sure the house is strong enough, but get the biggest cavity we possibly can, and we can do that by eliminating wood. It really winds up being just about the same price as framing in 2x4s on 16-inch centers.
You go to 2-foot centers.
You sure do. You can also get rid of a lot of wood at the plates at the top of the wall by framing with single top plates and putting the trusses directly over each of these studs. The other thing is that you're going to be temporarily diagonally bracing this wall because there's no exterior sheathing that's structural. And I want to show you what we're using. What this builder is putting over the exterior of his frame is an insulative sheathing, which takes the place of the plywood. It really does restrict the flow of heat through the various members in the wall. It's a good thing to do. Tell me what that piece of wood's for.
Makes the corner square. You can put the drywall on. I don't know.
It's really primarily there to hold the drywall. This could be completely removed and drywall clips could be used there instead, giving us more room for insulation.
Right, it'd be hard to get that insulation into the frame there too, wouldn't it?
It'd make it a lot easier. Let me show you another area in the frame where this builder has made an adaptation in his framing technique to put in more insulation. David, normally this rafter would be sitting right down on top of that top plate in a conventional construction. We realize that we've got to get more insulation over the top of the wall, which is a very significant thermal bridge in the building. We've got high levels in the attic, high levels in the wall, but it's the joint between the two that really matters. So this builder has insinuated a collar tie and this plate to tie the assembly together between the rafter and the top plate to give him more room for insulation.
That seems like that wouldn't be any particular big deal, just a little bit of thought and a minor change. Is that right? Are there other places you can make simple changes like that?
Sure can. We've already seen the treatment in corners. Lintels are a very good example also, where it's very difficult to get insulation. It's really important to remember areas where interior partitions come up to exterior walls. Lots of blind corners, which you really want to make sure are filled with insulation.
And this is all to get nice higher levels of insulation everywhere in the wall assembly, huh?
That's it. Listen, let's see you put that in there.
Not too tough, Oliver. I've done it before.
Yeah, but look, you want to remember that the way this stuff works is by trapping air in your wall,
You're being
right?
pretty picky there, aren't you?
Oh, no. You want to make perfectly certain that all of this is filling the cavity completely so you don't get any convection currents in there. You want to trap the air. You also don't want to have the insulation compressed in any way. You want to make sure that it's filling everything to do its job properly.
So you put it in nice and fluffy, not just to be a perfectionist, but to actually make it effective. Well, is that it for insulation? Is that the real key to putting it in?
Well, keep in mind that this is the same material that your furnace filter is made out of. It's fiberglass. You want to make sure you don't get air drawn through that material in order to make sure that the air trapped by it is going to be still. So you need a wind barrier on the outside of the building to prevent wind from blowing into the insulation, and you're also going to want an air barrier on the interior of the building to prevent air from inside entering the wall. As well, you don't want water vapor in there, and in this case, this is an air and vapor barrier.
Now, will I increase my effectiveness of my building if I put more insulation into this cavity?
No, if you compress this material, you will get slightly higher R values initially, but as you compress it, you just simply are throwing your money away. You want to make sure that the bat is going in there, completely filling the cavity, but it's no more full than necessary.
Well, how do you increase the insulation value then? Do you have to use thicker studs or something?
Well, that's one alternative, but when you're looking at a single stud wall, it's unlikely that you're going to want to go higher than, say, a 2x6, which is a practical weight for guys to lift into place and that sort of thing. So given that limitation, you could put heavier thermal insulation on the exterior of the wall, insulative sheathing, or alternatively, you could strap the interior. And if you strap the interior, you then create a space into which you can put additional insulation before you put the finish on.
Okay, well, that piece of wood you picked up is a 2x2. Can you use thicker? I mean, well, how do you tell how much insulation to put in the wall? What's optimum?
Well, there's an easy way for me to show that to you back at the office.
So the challenges to the builder just keep right on coming. You have to be a computer specialist now.
Well, I don't know about a specialist, but we're finding that computers are entering the industry more and more, and they're really useful. You can do payroll on them, inventory on them, costings on them, but what we use them for in this office primarily is to run the HOT 2000 program, and what that enables us to do is to get a heat load calculation without hiring an engineer. Here's an example of one.
Oh, I see. Listing all the different rooms, and what are the other things? Area?
Well, we've got ceiling, main walls, doors, basement walls above grade, basement walls at grade, basement floors. What we're able to do here is to put in the various areas of those segments of the building and the R values of that segment.
Oh, of each room.
Of each individual component. And what we wind up with is at the bottom a month-by-month heat load calculation. So that will enable us to figure out exactly what this building is going to heat for within reason.
So you can just for the heck of it try out more insulation in the basement, and then the computer resorts everything for you.
Exactly. You put in one building, and then by changing a single individual component, the R value of the windows or the doors or the basement floor, you can see immediately what impact that's going to have on your heating bill. And as well, it tells you whether it's going to be heated electrically, natural gas, oil, propane. You have a variety of choices that you can make. As a result of that, you can figure out whether it's cost effective to spend that money on the additional insulation or the upgrade in that area.
Well, you've convinced me.
It's also a very, very good tool for convincing clients, because when they see the level of care and attention that the builder has gone to in looking at the various components of the building, they recognize that spending a little bit more money up front in some component may really pay off in the end. We've covered a lot of ground here. Is it possible, do you think, for you to review it?
Ooh, my turn to review, huh? Okay, well, we started with the building design and then looked at its relationship on the lot for passive solar. And then looked at reducing heat loss with not only with a thick insulating blanket, but with an insulating blanket that is continuous and has reduced thermal bridging.
And then I showed you how you can use the HOT 2000 program to go through those items individually to ensure that you're getting the most cost-effective approach possible.
What have you got in mind for the next show?
Well, the next time we're together, what I'd really like to do is show you the flip side of the coin for heat loss, which is air leakage.
Well, Oliver will